Welcome to the first week of Calculus 1 course. Today we will do a review of important material related to the functions. Calculus is study of change. In a first year calculus course, we describe changes using function of a single variable. Typically, we will have y equals a function of x. A function is defined as a rule that associates with every input x or output y. There is only one output for every possible input. All the possible inputs x are known as the main, and all the possible outputs y we refer to as a range of a function. There are three forms of how function can be defined. We can be either given function using analytical formula. Here's an example. Y is equal to fraction, numerator is 1, denominator is x minus 1. If we record the possible values of x and corresponding output values of y in the form of a table, we have defined a function using tabular form. When we graph all the values of x and corresponding values of y in xy plane, we define this function graphically. In this particular example, a rational function y equals 1 divided by x minus 1 has an interesting domain. Because division by 0 is undefined, x equals 1 is not part of the domain. This is why in the table you see when x is equal to 1, y is undefined. For all other values of x, using the formula 1 over x minus 1 equals y, we can calculate for every value of x and output y. When we graph all these points, x and y, we notice how as x gets closer and closer to number 1, the y values either grow into plus infinity or they go to negative infinity. The y values either increase without the bounds or decrease without the bounds. We also can see that as input values x grow larger and larger and larger, the value of y grow closer and closer and closer to 0. Same behavior we notice as x grows smaller and smaller and smaller, minus 3, minus 4, minus million. The values of y also get closer and closer and closer to 0. In high school, we already learned that rational function 1 over x minus 1 has two asymptotes. One is horizontal, y equals 0, and one is vertical, x equals 1. When we have a graph of a curve in front of us, it's much easier to see if the given relationship between x and y is in fact defining a function y equals f of x. And we can use vertical line test in order to confirm that every value of x produces one output value y. There are several very useful basic functions that we will rely on when we're learning calculus. In our studies in grade 12, we have worked with lines, quadratic functions. Both lines and quadratic functions fall into the larger category. Those are polynomial functions. So any polynomial function looks like a constant multiplied by x raised to positive integer power, plus another constant multiplied by x raised to a different positive integer power. When you look at the highest degree of x, let's call this number n, we will look at the polynomial of degree n. So quadratic function that is written as y equals to ax squared plus bx plus c is a polynomial of degree 2. A line y equals mx plus b has x raised to the power 1, so n is equal to 1, and line is an example of a polynomial of degree 1. Another very useful function, the one that we just worked with when we looked at y equals 1 over x minus 1, is a rational function. A rational function can always be written as a fraction where we have in numerator a polynomial and in denominator is another polynomial. All polynomials have a wonderful, easy to remember domain. X can be any possible number for a function. Rational functions may have some restrictions on the domain. We know how the polynomial qx standing in denominator of a rational function cannot be possibly equal to 0. Another very important function to be able to recognize and work with is an exponential function. Exponential function has always the same shape. It's a base constant a raised to exponent x, where x is a variable. A constant can be any positive number not equal to 1. Logarithmic functions and exponential functions are very closely connected. They are inverses of each other. Logarithmic function is the one that you might find little problems with if you haven't practiced enough. It is important to review the properties of logarithmic functions and be able to work with them. When working with the functions, we need to be able to graph any function. And just as an example earlier, we can always take any function given in analytical form, create a tabular form for it, and then develop a graphical representation. By knowing how the graphs of the function look like, we can easily analyze what happens with the output of a function if we observe a change in the input. Let's take a look at the quadratic function. At x equals 0, y is equal to 0. If I'll change the input values of x, making them larger, x squared equals to y produces y values that are larger than 0. If x equals 1, 1 squared is 1. If I'll increase x to 2, 2 squared is 4. And if I continue increasing values of x to infinity, notice how the values of y also go to infinity. So we can observe from the graph how the changes in x result in changes in y and what the output of the value y wants to become equal to. Looking at the graph y equals absolute value of x, we can see that if I'll start with the x value not equal to 0, let's say x equals to negative 5. Absolute value of minus 5 is 5. If I'll change the input values from minus 5 to numbers closer to 0, say minus 4, minus 3, minus 2, minus 1, minus half, and so on, getting closer and closer and closer to 0, we're able to see that the output values of y also changing, getting closer and closer and closer to 0. Input minus 3 produces 3. Input minus 1 produces 1. So as we get closer and closer to 0 with the inputs, the output values y also get closer and closer to 0. It becomes very useful to have a graphical representation or idea how a function looks like when we're studying the changes in the function, changes in the processes. Studying how output values of y changing as we're changing input values of x is extremely useful when we're trying to analyze the behavior of a function and determine if function has any asymptotes. If the output values of the function get larger and larger as x approaches closer to some specific input value k, then the vertical line x equals k, a vertical asymptote. If the output values of the function are getting closer to a number k, as x gets either larger and larger and larger going to plus infinity, or x gets smaller and smaller and smaller getting to minus infinity, then the horizontal line y equal x is known as a horizontal asymptote. We have seen vertical asymptote and horizontal asymptote in this example of a rational function y equals 1 over x minus 1. Let's take a look at the other basic functions and see if we can find any vertical or horizontal asymptotes for another typical type of a function. As you can see, a quadratic function has no horizontal or vertical asymptote. So with absolute value or the square root. Rational function y equals 1 over x has both horizontal and vertical asymptotes. For the exponential function y equals a to the x, where a is greater than 1, we notice how output values of function a to the x get closer and closer to 0 as x input values x go to negative infinity. Horizontal line y equals 0 is a horizontal asymptote of an exponential function a to the x. Logarithmic function, when the input values x get closer and closer to 0, while still being positive numbers, the output values y decrease, going to negative infinity, which means that vertical line x equals 0 is a vertical asymptote of a logarithmic function y equals logarithm of x with the base a. In calculus, we will use the functions we looked at today many times, solving equations that have exponential, logarithmic, or polynomial functions in them. If you don't feel comfortable with any of the properties of exponential logarithmic functions or do not know how to find roots of the polynomials, this is a perfect time to start reviewing this pre-calculus material. Please work through the posted questions, and if you have any concerns or any questions, come to the class. We'll continue conversation there.